All right, here we go for section 3.5. This is a 6-page set of notes, so this video might be a little longer than some of the others, but it shouldn't be terribly longer. All right, so in 3.4, which was pretty short, we looked at circles and how arc length is connected to angles at the center of the circle. We used radians, that sort of thing. Now we're going to take those same sorts of ideas, distances along the edge of a circle, and things are going to move. All right? So in this picture that we have here to start, we just have, imagine here's point P, and it's like it says, wow, going around the circle. And as P moves, or if P is not moving, this point is moving. P is where we're measuring from. You could almost think of this as like positive x-axis or something. So we have this one side, and we're measuring the location of this point from there. So the distance that that point covers as it goes around and the angle of its position, both are changing. So we have an arc length that's changing and an angle that's changing. Now, when we do this, there's two different ways to talk about how fast things are changing when stuff is moving circularly like this. We have angular velocity and linear velocity. Now, linear velocity is the one we're more used to, although angular velocity shows up in plenty of situations too. This is the kind of velocity that your car's speedometer tells you about. This is just straight up distance being covered by a moving object. Right? We use a V for it, and the formula is really, this is rate, distance, time, and in terms of the labels we have for circular motion, V equals S over T. All right, how far did you go divided by how long it took? That's what velocity is. And we're talking about units of miles per hour, meters per second. Basically, any sort of length unit divided by any sort of time unit is a linear velocity unit, right? The other type of velocity we have is the one that gets at the fact that we're talking about things moving around in circles and gets at the how much rotation has occurred, all right? Angular velocity is what we're talking about. Now, the symbol we have here, it looks like a W, but that's actually a lowercase omega. Lowercase Greek letter omega. And just like we often use Greek letters to measure angles, since this is measuring how fast an angle is changing, we're using another Greek letter. All right. And the formula for angular velocity is similar. It's amount of something changed divided by how long it took. And so here we have a change in an angle, how much something rotated, divided by how long it took for it to do that. So angular velocity is some angle measure, or some measure of rotation, divided by time it took. Now, we don't have a whole lot of units for measuring angles or rotation. We have radians, we have degrees, and I'll get to RPMs in one sec. But all of these are some angle measured, the units at least, are some angle measured divided by a time unit, seconds, hours. RPM, of course, stands for rotations per minute. So another way that you can measure the amount of rotation is just to actually measure full rotations. So this R is rotations. So not degrees, not radians, but just full-blown, complete rotations. And the M is minutes. RPMs being the typical measurement for the speed of an engine. It was the old measurement for old records and how fast your turntable should rotate. It was measured in that unit of RPM. Okay. Now, these are separate ideas or separate notions of velocity, but they actually connect together quite nicely. Like we saw in 3.4, arc length is just radius times the angle it goes with in radians. All right, and because those two are related like that, we get a nice little sequence here. So like we said up above, V is S over T. So we'll replace the S with, R over theta, or sorry, R times theta, right there. Well, I'm just going to bump the r off the top of the fraction so it sits next to the fraction. But theta over t, well, that's exactly this thing called omega from up above. So if we make that replacement, we get this nice relationship. Linear velocity, v, is just the radius of the circular motion that we're talking about times the angular velocity that's involved. All right. Now, when we use s equals r theta in the previous section, one of the key points about that was that theta had to be in radians for this formula to work. All right, and just like that has to be true, if you want to use v equals r omega, omega needs to be in a unit involving radians. All right, now omega is angle measurement per time, so it doesn't matter what the time unit is, but it can't be degrees per second or rotations per minute. It needs to be radians per some time unit. So sometimes one of the little chores we got to go through to solve a problem is making sure our angular velocity is in radians per something. And that's what the blurb at the bottom here says. Okay, I'm going to switch to the blank version and we'll start working on some problems here. So page 2, here's our first problem. A satellite in geosynchronous orbit. So goes in circles around the Earth. We're going to find out how fast this guy is moving. Now, there's one important word here that is key for this problem, and that is geosynchronous. All right, now some satellites are in a geosynchronous orbit, so its orbit is synchronized with the Earth, where the geo comes from. So in other words, it's always above the same point of the Earth. It orbits, so it goes around the Earth one time at the same rate that the Earth rotates. And satellite TV kind of satellites are in a geosynchronous orbit, and that keeps them in the same position up in the sky relative to where you are. It wouldn't make a whole lot of sense for your TV satellites to just go around the Earth and be in different spots all the time, because we try to point those dishes right at the satellite to get the best reception. So actually around Michigan, if you look at DirecTV dishes and things like that, they all point in pretty much the same direction, kind of southwest-ish, I think. We don't actually have one. But if you look around, they're all pointing at where the satellite is to get its signal, and that satellite is in the same place. Right? Satellites go around the Earth at different speeds based on how far from the Earth they are. Those two things go hand in hand. And in order to be in a geosynchronous orbit, you've got to be about that far above the surface of the Earth, 20,000 miles away. So if we actually draw a picture of this, there's the Earth, and our satellite is way out here, where this distance is 4,000, and this distance is the 20,000 in the problem. So in terms of the radius of circular motion, that would be the whole length of this segment, and our radius is the 4 plus the 20, so 24,000 miles. Now, when we're asked to find linear velocity, we're talking about v. Find v. And our nice little formula is v equals r omega. We've got r, so it is just a matter of writing down omega in terms of radians, and we'll be all set. Now, geosynchronous is what tells us about the angular velocity. So what we know is that a satellite in geosynchronous orbit takes 1 day to go all the way around the Earth. So in other words, we have one full rotation in 1 day. All right. So now, the only issue here is the fact that this is not measured in radians, and it needs to be, but we know one rotation, one full rotation, is the same as 2 pi radians. So while we are dealing, in the previous sections we dealt with converting between radians and degrees, we also have this third unit for rotational movement measurement, and that's just flat out rotations. We need to know those, be able to convert between those as well. So, making that change, this is the same as 2 pi radians on top in 1 day. And what we're actually going to do, just to make our velocity unit a little something that we're more familiar with, I'm going to turn days into hours as well. So in fact, we have 1 full rotation, 2 pi radians, in 1 day, which we know is 24 hours. So in other words, we have, if we cancel the 2, pi over 12 radians per hour is how fast the satellite is rotating. So what kind of speed does that correspond to? Well, now we've got omega, we got r, we can say v equals 24,000 times pi over 12. And if we cancel the 12 with a 24, we get 2,000 pi, which, if you simplify that or punch that out to actually see what we get, it's approximately, I'm going to give it a squiggly equals here, 6,300 miles per hour. So that's how fast those satellites are hurtling through space that far from the Earth. So that's the speed it has to be this distance from Earth. And actually, if you want to have an orbit that's closer to Earth, you have to go faster. If you're going too slow, Earth just pulls you in and you burn up in the atmosphere. So if you want to have a smaller an orbit closer to Earth, you have to be going faster. So in fact, the International Space Station is only like 150, 200 miles off the surface of the Earth, and it goes blazing around at like 17,000 miles per hour. And it takes an hour and a half to circle the Earth. It goes much, much faster, but it has a much, much lower orbit. Anyway, we could say a whole lot of things about this problem. We're just going to go to number 2. All right. Bike wheel, radius 29 centimeters. So immediately, r equals 29, and that's in centimeters. All of these sorts of problems, there are a whole bunch of different quantities going on here. There's a radius of our motion. There can be s, the distance covered as it moves. There can be theta, the angle that something rotates through. T, time involved, but then also v and omega, the velocities, how fast things are moving. And so we'll sometimes have these story problems which have a lot of stuff in them, and we really would like to sort through that, basically, and try to see what pieces of information are we actually given. So, for example, we know r equals 29. That's right there. And then we have this info, 43.5 meters. Okay, it's a distance, for one. It's not the radius, but it's just a straight-up distance. And that's exactly what S would be. How far did this object travel on its circular arc? And it happened in 20 seconds. That's clearly a time. Oh, I should put meters right here. Seconds. What is the wheel's angular velocity? So that's omega. We're going to try and find this guy. And how many full rotations did it make? All right, now angular velocity is a rate of change. How fast is something changing over time? But how many full rotations did it make in this 20 seconds? Well, that's just an angular measure. How much did it rotate? There's actually, I have oftentimes done 2 different solutions for this, and that comes from seeing what quantities we have and then using the formulas we know. How can we combine those together to figure out these other things? So I'm going to do one solution here, and you can look at the second solution in the notes too. And one may seem more instinctive to you or more natural. Neither one is necessarily better than the other. And sometimes funny things can happen when you round along the way. But there's, different ways to get to the same point. Now we have R, S, and T. And maybe the first thing you see is, well, like we said earlier, V is S over T. In fact, this whole line right here is kind of telling you how fast things are going. So V is S over T, so we would have, before that, one thing to notice. So we have 2 distance measurements here, a radius and an arc length. And as they're written, they are not in the same unit, and they very much need to be. So we got to change one to the other. I'm going to take the S and just turn that into centimeters, since that's a little cleaner, actually. 100 centimeters in a meter, so if we multiply by 100, we get 4350, like so. And that's in centimeters. Okay, so then I'll put 4350 centimeters over 20 seconds. And if we do that division, you get 217.5. And the unit on that guy comes straight out of the computation, centimeters over seconds. Hopefully that makes sense. We're computing a velocity, centimeters per second. There you go. Okay, so that gives us V. So how about getting to omega, or theta for that matter? All right, well, when V equals R omega, that's one of our main formulas here. So there's 3 letters in there, V and R and omega, and if you know 2 out of the 3, you can figure out the third one. So I'm going to rearrange this guy, actually. To get omega by itself, I would divide both sides by R, so omega is V over R. So I'm going to put in omega equals V, which is 217.5, over R, which we said 29. And if we put the units in, centimeters per second and centimeters, the centimeters are going to cancel. And we'll still have per seconds involved, so we'll get an answer, and it'll be something per second. Now, if we do the little computation, we get about 7.5. And you can ask, okay, well, this is an angular velocity, so it's got a unit of angle, change in angle, divided by time. Well, what angle measure comes out of this? Well, what happens when you use V equals R omega? If you put in omega, it needs to be in radians per something. If you use this formula to get omega out of it, it comes out in radians per whatever. So radians per second is how this comes out. All right. So that's how it comes out. So, and that could be, that's a legit answer to what's the angular velocity. Well, there you go, 7.5 radians per second. All right. It's not specifying a unit in particular. The other question here is how many full rotations did it make? Now, there's even 2 ways to go about this. We know this lasted for 20 seconds, and we were doing 77.5 radians per second. So, we wrote down earlier, omega is theta over t. And you could also use this formula to get theta. It's, again, another formula with 3 variables, and if you know 2, you can get the third. If you multiply both sides by t, theta would be omega times t. So theta, which is just a solid measure of how much something rotated, 7.5 radians per second times, we have 20 seconds in this situation. And so if you punch that out, 150. Now, what's our unit? Well, seconds on the bottom and seconds on the top would cancel, and it would just be measured in radians. Now, how many full rotations is that? Well, this is just a measure in radians, and like we used before, 2 pi radians in a rotation. So we need to multiply by. And we'll be dealing with lots of units here in lots of different places, and being able to handle these is an important skill. Now, we want radians to go away and rotations to appear. And we know that they're related by a factor of 2 pi, and the question is, does the 2 pi go on top or does it go on the bottom? Well, we want radians to go away. And so here's radians, and to cancel radians, we would then need to have radians on the bottom. And because of that, we would put the one rotation that is equal to 2 pi radians, we'd put that on the top. So we do 150, and we divide by 2 pi, and you get around 23.9 full rotations over this amount of time. Now, one important thing about using your calculator to do this sort of thing. This is especially true with like a calculator where you can type in a whole expression and then you hit enter. So like a TI-84 especially, stuff like that. If you type in 150 divided by 2 pi, exactly like that, and you hit enter, it's not going to give you the right answer. It's going to give you something that's a lot bigger. And that's because what your calculator reads is 150 divided by 2 and then multiplying by pi, which is not what we want. We have pi in the denominator. So if you want to make sure you divide by the whole 2 pi, you might need to put parentheses around there, and then you could hit enter. Or you got to do 150 divided by 2 and hit enter that, and then divide by pi after that to get the right answer. Okay, so in the filled out notes, which I guess I can just show you real quick, I have 2 solutions written up, and in fact the first solution is kind of like the one I just did, but even takes a slightly different path from there. The solution number 2 uses the fact that with the stuff we know, R, S, and T, you could actually figure out how much rotation occurred based on these things. Because if you know S and you know R, you can get theta. So that's what happens first here. So if you do that, you can do S divided by R. Again, you need centimeters. You need matching length units for those 2 distances. You get the 150 radians. Convert radians to rotations like I did. And then you could actually just divide by seconds and get down to a value of omega in terms of rotations. I'm actually noticing right now, a revolution and a rotation we pretty much take to mean the same thing. A full orbit of 1 trip all the way around. So I didn't even notice until right now that I used 2 different words for the same thing. Okay. I'm gonna do another example here yet. I don't know that I'm gonna do both parts of this because the second part is less important for what we're trying to do, but we'll do the first part for sure. Okay. Ferris wheel, radius 120 feet. The book, you'll notice if you read through examples or go through the textbook, really likes Ferris wheel problems. Ferris wheel has a radius of 120 feet. So here's our Ferris wheel. And the center is located 135 feet off the ground. Okay. So the picture would look something like this. And actually that 135 doesn't matter to us until we get to the second part. 1 full revolution takes 18 minutes. All right. Find the linear velocity. That's v. In miles per hour. All right, so if we imagine, if I can draw, there we go. We're going to think of the rider on the car starting here at the bottom and then rotating. And as it rotates, it covers some amount of distance. Here's our radius, which we know is 120. So R is 120 feet. So if we're going to find V, and we got R, ideally we would just like omega because we know V equals R omega. So, and this is telling us about how fast it's rotating. 1 full revolution or rotation in 18 minutes. So in fact, we know omega is 1 full revolution or rotation, and that occurs in 18 minutes. Now, you have to hesitate hesitate and don't give in to the urge to just multiply R and omega and be done with it because, like we said before, omega has to be in radians per something. So, Again, it's that factor of 2 pi. So do we multiply? Do we divide? What do we do? Well, we want revolutions to go away. So we need revolutions to be on the bottom, which means the 2 pi radians goes here up top. And so in fact, I'm going to cancel this 2 with the 18. And if we multiply through, where we still have pi on top, we would have 9 on the bottom. The revolutions cancel, and all we have left is radians on top per minute on the bottom. So omega is pi over 9 radians per minute. And you could punch that out if you want the decimal, but we don't need to. But now that omega is measured in radians, and here's our radius, we can say V equals 120 feet times pi over 9 radians per minute. So we can cancel a 3 out of 120 and 9, which would leave a 40 on top to go with pi. Taking 3 out of 9 leaves a 3. And the unit, well, we have per minute. And this is a linear velocity, so it should be a distance on top per minute on the bottom. And we have feet. But you may ask, well, what the heck happened to this guy? Well, radians they're kind of a funny unit in that they sort of disappear or appear when you use V equals R omega, or if you use S equals R theta as they're needed to. Radians are really just a ratio. If you think back to how we defined a radian, theta equals S over R, arc length divided by radius. This would be like measuring something in feet divided by something in feet, and the feet cancel and there's no unit. And the radian measurement really just indicates the ratio of an arc length to the radius. And that's where the 2 pi shows up, or why pi shows up there. So radians kind of are just a scaling thing to scale a radius into the corresponding arc length, which is what makes them kind of disappear when they're supposed to and reappear when they're supposed to. All right, so this boils down to, here's our answer then, our speed, 40 pi over 3 feet per minute. If we punch that out to give it some sort of meaning, that's 41.9 feet per minute. And you could possibly picture that sort of speed, that many feet, cover something moving that far in 1 minute. But it specifically says find our answer in miles per hour, which means changing a couple things. All right. In fact, we want miles on top and hours on the bottom. And to do that, well, there's 2 changes to make. Feet need to turn into miles. And there are 5,280 feet in 1 mile. So do you multiply or divide by that number? Again, if you can't straighten that out in your head, just think about units getting canceled. So here's feet on top. We want to get rid of feet, which means 5,280 feet on the bottom would go with the 1 mile that is equal to it. And now we want minutes to go away and hours to appear. Okay, well, we can put 1 hour on the bottom. How many minutes in an hour? We know that's 60. And so if we take 41.9, we divide by 5,280, and then multiply by 60, you get 0.48. And now our unit is miles on top and hours on the bottom. Miles per hour. So half of a mile per hour. Not very fast is how fast this guy rotates. All right, I'm going to ignore the second part of this, so we're just going to skip that. And we're going to get to, I think I might cut this video into 2. We're going to finish this page and do letter E at the top of the next page. As you may have seen, one of the major tasks here, and sometimes the major difficulty that students have, is dealing with angular velocities and the units that are involved and turning that into an expression for an angular velocity in radians per something. All right. So here, number 1, A, B, C, D, and E, and then there's E and F at the top of the next page. Here are 6 expressions of angular velocity, how much something has rotated. turn that into an angular velocity that has radians per something. All right? I'm going to just do the first one for you. 200 degrees per minute. All right? So 200 degrees per minute. The minutes are fine. That's not a problem. It's the degrees. We want radians. All right, well, it's pi over 180 or it's 180 over pi. Which one is it? Well, when you think about converting, it's 180 degrees, the same as pi radians. If we want degrees to go away, we'll put 180 degrees on the bottom, and we'll put pi radians on top. So we're going to do 200 times pi divided by 180. You can cancel a little bit and get 10. Take out a 20 from 200 and 180. 10 on top, the pi's on top. We have 9 on the bottom. And if you actually punch that out, it's about 3.49. But now our unit would be, we've got radians instead of degrees, and still have minutes on the bottom. So radians per minute. Okay. Why don't you give B, C, D, E, and F a try and see how they go. I'm going to do a few more of them, but then, of course, the conversions are all in the filled-in version of the notes as well. So if you want to, and I think you should, pause the video, give them a shot, see how they go. But I'm going to do a couple more of them right now. So here goes. Letter B would actually be similar to A. You're just turning degrees into radians, but dealing with the fact that there's 4 seconds on the bottom. 16 rotations in 3 minutes. Well, that would be literally 16 rotations over 3 minutes. All right, minutes are fine. Rotations need to change. 2 pi radians in a rotation. We want to cancel rotations, so we'll put 1 rotation on the bottom and 2 pi radians on top. And we would actually, if we multiplied it all together, 32 pi over 3, which you could punch out, 33.5, and now we have our radians, the rotations canceled, and minutes on the bottom, so radians per minute. Letter D, you can see the solution, but an orbit is a full rotation, so we're saying half an orbit over 5 hours. A complete circuit is also just another name for 1 full rotation. So omega is a full rotation over 12 minutes, and you convert that to radians. You can see it in the other one, or in the filled-in notes. 3,000 RPM. We are talking about 3,000 revolutions per minute. So 3,000 revolutions over 1 minute. All right, times, convert to radians. 2 pi radians in a revolution, or a rotation. And we want revolutions to go away, so 1 revolution goes on bottom to cancel the revolutions up there. It's equivalent to 2 pi radians. So we're talking 3,000 times 2, 6,000 pi. Or in other words, what does that work out to be? It works out to be approximately that many, and now we have radians on top, and we still have minutes on the bottom. And that'll do it. All right. I'm going to stop this video because I don't know how long it is already, and I will do a second one for the rest of 3.5.